Welcome to yet another new lecture on gas cycles in thermodynamics as part of Basic Mechanical Engineering 3. The content in this lecture is going to be basically we will try to introduce gas power cycles. Basically using gas, how does a power cycle runs, that means to say how do you generate power. Then we will try to look into air standard power cycles, then Carnot cycle, Stirling cycle, Otto cycle. Otto cycle you know it is used in automobile, then diesel cycle, then comparison between the actual diesel and Otto engine. Then we will try to see dual, that means to say mixing of two, dual combustion cycle, then comparison of Otto, diesel and dual cycle. Then finally, we will try to see Brayton cycle and the derivation which is associated with actual cycles. Gas power cycle is a thermodynamic cycle that uses gas as its working fluid to convert heat into a mechanical energy. That means to say the gas is heated, right, and it is taken to a higher temperature. So, to start up, what happens is you try to take the air inlet, right, the air goes inside, then it is getting compressed, where the pressure increases and then it was allowed to go through a carburetor where there is a mixture of fuel and air happens. Then after this it is burnt and it is sent to turbine. So here the T increases, P increases. Here what happens? P decreases and the T also decreases. By doing so, it is trying to turn the turbine blades. Now, when it tries to turn the turbine blades, the output of the turbine blade is taken to a gearbox where they have a ratio 1:5, 1:10 or something. So, they accelerate or they amplify. Gearbox is nothing but a mechanical amplifier, or you can say multiplying agent or a dividing agent. So, you can increase it or decrease the speed, and wherein which you try to make a compromise on your torque. So, then gearbox is attached. From a gearbox you try to take it to a generator, right. This generator, electricity whatever is there is sent to a substation. From a substation it transmits, right. So, now we have left the story here. So, what happens to the gas which is there here? So, this gas whatever is of very high temperature. So, it tries to heat the water which is through this pipe, right. It is water through this pipe. So, now water whichever is there is getting heated and it converts into a steam. The steam is generated through this pipes and this pipe is trying to take it to a steam goes up and from there it goes to a boiler. So, in a boiler there is a transfer of heat which is happening. So, if you look at it, it is a closed loop. So, there is water. Okay, let us take water from here. There is water coming from here. So, then it is the water is getting treated. The treated water is going through a pipe and this pipe is going to a steam boiler. So, here there is a cold water and now whatever is heat there on the top, it is throwing the heat now. So, there is a transition happening between the cold and the hot. So, whatever it is the hot, so then that tries to come into high pressure and high temperature, it comes through this pipe and then that tries to hit the turbine blades. Through this turbine blades again gearbox to generator. Okay. So, now you can see here there is generator 1, generator 2, a larger turbine, a smaller turbine. So, whatever is the steam gets condensed and if it is still heat, then it is sent to a sink where it is passing through a coolant tower and it comes to room temperature. From the cooling tower, it gets back into the sys circuit. Okay. So, you can see here steam is getting condensed. So, whatever comes from here, the condensed steam becomes water and that water goes here. So, then this is a independent circuit, cooling tower, this is an independent circuit, you see here. So, the water whatever comes from here gets deposited down and it goes into the reaction, and while the heated water, the steam comes down, this is trying to do a heat transfer to this liquid whatever is there, that liquid gets cooled through the cooling tower. Why? Because whatever comes down, if it goes with a very high temperature, then here there will be one more amount of boiling. So, this becomes an independent circuit. This is another circuit, but it is connected to the previous one, and this part is completely a different one. So, there are 3, 1, 2 and 3. The third system is only to cool. The second system is a small version of the large system. Okay. So, the gas power cycle are fundamental to modern mechanical and aerospace industry, forming a backbone of numerous power generation and propulsion systems. So, in aerospace, we always use gas power cycles. So, basically you will have all these things, and if you see this, very simple, you have a working fluid called water. So, this water will be converted into steam. When you convert into steam, what are there are only two possibilities. One, you increase the temperature. Next is you have to play something with the pressure. So, these are the two things, and if you assume that it is a closed loop system, there is no change in the volume of water. So, the water when heated becomes steam. When it is steam, the temperature goes high, and in between what you do is you try to pass it through a turbine or you try to pump it faster, the pressure also goes very high. So, when this temperature and pressures are very high, now you have to bring it down to normal temperature and pressure. So, when you have to bring it to normal, you have to do work. So, that is how the work is done here, that is all, nothing more. Now, I think you should be able to understand. Now, you replace water by gas, that is all. So, water, steam, temperature, pressure, increase, decrease. So, when it is increased, you try to heat it. When it is decreased, you try to convert it into a normal water and then take it back into the system, right. The gas power cycles are fundamental to modern mechanical and aerospace engineering, forming the backbone of numerous power generation and propulsion systems. These cycles describe the thermodynamic process by which heat energy is converted into a mechanical work using a working fluid. That is what I said. You have a working fluid, this working fluid you are trying to play with pressure and temperature, that is all. So, typically air and combustion gas which remains in the gaseous state throughout the cycle. The gas power cycles are idealized models that helps the engineer understand, analyze, optimize real life engines such as internal combustion engine, jet engine and gas turbines. They are categorized both into open cycle and closed cycle, with the Otto, Diesel, Brayton and Atkinson cycle being the most prominent one. Each of these cycle models a different type of engine operation, capturing the essential thermodynamic steps such as compression, combustion, expansion and exhaust. 4 steps, very easy. You have air, this air has to be compressed. You have air close to volume, it has to be expanded, right. Then when you compress and when do you switch to expansion? There has to be a process called as combustion, blast, combustion. Once this combustion happens, the expansion happens, whatever is left out in the system has to be exhausted. 4 systems, 4 steps, right. When you talk about compression, expansion, you will try to have a PV diagram, you will try to have a TS diagram, straight. By analyzing these processes using assumptions like ideal gas behavior, isentropic, we have seen all these things, isentropic efficiency, constant specific heat, engineers can predict the engine performance metrics such as thermal efficiency. This is very important. In the examination, you will be asked only these things. How do you calculate thermal efficiency? How do you calculate the work output? How do you calculate the specific fuel consumption? Specific fuel consumption is 1 liter of petrol or 1 liter of diesel, how far it is going. For example, how many kilometers it is going. That is specific fuel consumption. Right? So, these are the 3 outputs we used to take in the system, wherein which we assume that it is an ideal gas behavior, isentropic in nature and constant specific heat. Although ideal gas power cycles simplify real engine behavior, they provide crucial insight into the trade-off involved in engine design, such as balance between efficiency, power and complexity. So, here when I talk about thermal efficiency, we also try to calculate work output, we also try to calculate power output. This is also there. The power cycle continuously converts heat into work, in which the working fluid repeatedly performs a succession process. Why? Because water, it is a closed loop system, water heats, steam, you cool, becomes water, then you heat, it continues in a cycle. In the vapor power cycle, the working fluid, which is water, undergoes a change in phase. What is the phase? Liquid phase to gaseous phase. With growing demand for energy efficiency and environmental sustainability, understanding gas power cycle remains a cornerstone in developing advanced, cleaner and more efficient systems. In addition to this foundational role in engine design and thermodynamic analysis, gas power cycle serves as essential tool for evaluating the performance limits, efficiency potential of real world machines. The power cycle are those thermodynamic cycles in which heat energy is partially absorbed to produce net mechanical energy. The power cycles can be classified easily into 2, gas and vapor. In gas cycle, we use gas as a working fluid. The gas does not undergo change of phase. So, IC engine and gas turbine, they work on gas. When we talk about vapor pressure, we always try to take water as a working fluid, right? Water as a working fluid, but sometimes you can use other chemicals also. They use vapor as the working substance, and the vapor undergoes a change in phase. That is why it is called as vapor power cycle. So, steam engine, steam turbine. So, these are different. The power cycle which assumes air as a working fluid is known as air standard power cycle. So, we saw vapor, we saw the gas, right? 2 systems we saw. Now, we are trying to say we assume air. In the vapor, we try to take a liquid where there is a change in phase. In gaseous, we try to use gas as a fluid, and where there is no phase change, gas cannot do a phase change, right. So, of course, if you can go in the negative temperature, then it can become a liquid. When you go further down, it can never become a solid, but it can become a liquid very fast. So, the power cycle which assumes air as the working substance is known as air standard power cycle. The following assumptions are made for the analysis of air standard cycles. The air of fixed mass undergoes a cyclic process. Air of a fixed mass, air in mass. The air behaves like a perfect gas. It does not have any molecules, it does not give any friction, there should not be water, all those things. The specific heat of air remains constant all through the cycle. It is an assumption. The thermodynamic process of a cycle are reversible. The combustion process is replaced by heat addition process from an external source. The combustion process is replaced because when combustion happens, so from compression, combustion, expansion will go, right, and then exhaust. You try to apply heat from outside. The exhaust process is replaced by a heat rejected process which brings the state of the air to the initial state thus completing the cycle. So, as I told you, compression, then it is combustion, then it is expansion, then it is exhaust, right? Compression and this is combustion, right? In combustion, there is a heat addition. Exhaust, there is a heat rejection. The compression and expansion process undergoes reversible adiabatic process. So, the air standard power cycle system looks like this. So, you will have, this is a cylinder, the internal of a cylinder is called as a bore. Cylinder, the hole, right? You have a water bottle, the inner side of the water bottle is called as a bore, right? Then what will happen is there is a piston which is to prevent the air which is stored inside the bore to be constant, right. So, the piston is a moving member. So, depending upon the heat, there can be an expansion, or when the piston movement, there can be a compression. So, for the air to come into the system, you have an inlet valve, and for the exhaust to go out, it is called as the exhaust valve. So, the top one is called as TDC, top dead center. The bottom one is called as the BDC, bottom dead center. So, what it means is the piston can go very close to the top dead center, and the piston can come to the farthermost in the cylinder is the bottom dead system. The complete distance between the TDS to BDS is called as the stroke, right. So, when the piston is at the topmost position, there will be almost 0 air. So, now what happens when the piston is moving down, it is opening the inlet valve and it is trying to suck through inlet valve the air inside the system. And once the piston is returning back to the TDC, the exhaust valve will be open and all the things which is burnt out will be thrown out. Okay. So, this is the air standard power cycle. So, again here compression, you will have combustion, then you will have the expansion, then you will have exhaust, 4 stages. Okay. So, here if you see the TDC is in the top, the BDC at the bottom. So, this one is called the total volume, this is the length, stroke length. Okay. The total volume of air which it can take is called as a displacement volume. So, between the TDC and the cylinder top end, between this is this thing, and here it is called this one is called as piston, right. So, this one is, this small area is called as clearance volume. Okay. These are the terminologies which are used in reciprocating engines. So, some of the important terminologies related to reciprocating engines are shown in the figure. Bore, the diameter of the piston is the bore, true, because whatever is there, the piston also, because if you do not have the piston tight, then there will be air leak which is happening. Okay. Some important terminologies related to the reciprocating engine are shown in the figure and are explained as follows. Bore, it is the diameter of the piston. Top dead center, it is the position of the piston when it forms the smallest volume in the cylinder. So, it is the top dead, smallest volume. And when you say stroke, stroke is the distance between the top dead center and the bottom dead center, and the piston travels one stroke, one direction. The length is called as a stroke. Then what is intake valve? It allows the air or the air fuel mixture to be drawn into the cylinder. It allows the air inlet valve. It allows the air or the air fuel mixture. Air is plain air. Air fuel mixture means air plus some volatile material when it enters inside. Air fuel mixture to be drawn into the cylinder. Then exhaust valve, it is after the combustion is over, it allows the combusted product to be expelled from the cylinder. So, then there is something called as a clearance volume. The clearance volume is the minimum volume from the cylinder when the piston is at the topmost position or top dead center. The displacement volume is the distance between the TDC and the top end of the BDC, is the volume equal to the difference in total volume and the clearance volume. Swept volume is the piston moving from TDC to BDC or BDC to TDC. When there is a moving and expansion happening, so then there is something called as compression ratio. So, the compression ratio is given as RC. It is the ratio between the maximum volume to minimum volume formed inside the cylinder. Maximum volume divided by the minimum volume in the cylinder, that is the ratio. Okay. So, all these things till we have seen is part of air standard power cycle. Right. Here there are 4 processes, that also we saw. Next, let us get into Carnot cycle. Carnot cycle is a totally reversible cycle consisting of 2 isothermal and 2 isentropic process, wherein which this isentropic process is always a reversible adiabatic process. The Carnot cycle can be executed in a closed system or a steady flow device. In this cycle, either we use gas or we use vapor as the working fluid in Carnot. So, the Carnot cycle is the most efficient cycle that can work between the heat source T1 and the sink T3. It is a most efficient engine is Carnot engine. The Carnot cycle cannot be built in reality because it is not a practical cycle. However, Carnot cycle is used as a standard as against which the actual and the ideal cycles are compared. Okay. So, Carnot cycle is again divided into the 4 processes: isothermal heat supply, isentropic expansion, isothermal heat rejection, isentropic compression. When there is a heat source and when the cylinder at its topmost position, what is happening, there is a heat which is applied, then immediately what will happen, this piston will start expanding. So, there is a increase in the volume. So, the piston keeps moving down and then the piston further keeps moving down when the 2 to 3, when there is an isentropic expansion. After reaching the state 3, now what is happening, there will be a heat which is getting rejected. So, the piston is moving towards up. So, there is 3 to 4, there is a compression, and 4 to 1 there is a other compression. So, 3 to 4 is isothermal heat rejection because heat in, Q out. So, isothermal heat rejection, and the other one 4 to 1 is isentropic compression. So, the TS diagram for the entire system is drawn here. T is constant from 1 to 2 and 3 to 4 the T is reduced. So, from 1 to 2 there is a constant temperature and the entropy changes. From 2 to 3 there is no entropy change, but the temperature drops down drastically. From 3 to 4 there is a constant temperature and there is a heat which is getting rejected, and 4 to 1 is the isentropic compression, wherein which the entropy is the same. So, isothermal expansion, in this process the gas is placed in contact with the high temperature heat source and expands slowly while maintaining the constant temperature TH. As it expands, it absorbs heat energy from the source. Since the temperature remains constant, the internal energy of the gas does not change and all the absorbed heat is converted into work done by gas on the surrounding. So, since the temperature remains constant, the internal energy of the gas does not change. The internal energy of the gas does not change and all the absorbed heat is converted into work by the gas on the surrounding. So, that happens during isothermal expansion. 1 to 2 heat is in. 2 to 3 there is an adiabatic expansion. Next, the gas is thermally insulated. So, there is no heat can enter or leave the system. It continues to expand and is doing so, its temperature falls from TH to TC because no heat is added or removed. The gas uses its own internal energy for working. This results in decrease in temperature and pressure, but the entropy stays constant, because this is yes, this is yes. The 2, 3 is constant, 4, 1 is also constant. The difference is delta S. Next is isothermal compression, 3 to 4. Now the gas comes in contact with the cold reservoir at constant temperature Tc. It is slowly compressed, and during this process it releases heat to the cold reservoir. The temperature of the gas remains constant throughout. So, the work done on the gas is equal to the amount of heat it gives away. Again, the internal energy does not change, U does not change. The last one is going to be adiabatic compression. Finally, the gas is again insulated and it is compressed without exchanging heat with the surrounding. As the gas is compressed, the temperature increases from Tc to Th. The work done on the gas increases its internal energy, raising both its temperature and pressure. The process ends where it begins and completes a cycle. So, this is what it is: 1 to 2, 2 to 3, 3 to 4, 4 to 1. Heat rejection, heat addition, heat rejection. This is compression, and this is expansion. Now, let us try to refer to PV diagram and TS diagram. So, this is PV diagram. PV diagram we can and TS diagram we can see heat supply is Q supply. Q supply is nothing but Q1 minus Q2, which is RT1 natural log V2 by V1. Then what is getting rejected is between 3 and 4. So, you have this. So, for the process 2, 3 where there is an expansion, it is V2 by V3 is equal to T3 by T1 to the power 1 minus gamma minus 1. And this is nothing but V2 by V1 is equal to V3 by V4. The efficiency can be calculated as efficiency is equal to 1 minus Q reject by Q supply. Right. So, Q reject is here, Q supply is here. So, you solve this equation and finally, what you get is eta efficiency is equal to 1 minus T1 by T3. So, if you see here V2 by V3 only we say 2 to 3, V2 by V3 equal to T3 by T1 to the power 1 by gamma minus 1. So, this implies that V2 by V1 is equal to V3 by V4. So, Stirling cycle. Stirling cycle consists of two reversible. See, here also we saw it is Otto cycle is also reversible, totally reversible cycle. Stirling cycle consists of also two reversible isothermal and two constant volume isochronic process involved. It is a totally reversible cycle like Carnot cycle, as the heat addition and the heat rejection processes takes place isothermally during the cycle. The heat rejection and the heat addition and heat rejection process takes place isothermally during the cycle. Say for example, you have a piston, right? You have a cylinder has open end. So, you have two pistons, these pistons move, right. So, here you have air is at a temperature T1, then you have a regenerator stationary, right, and then you will have pistons P1 and P2. So, this moves this side. The working of a Stirling cycle is a closed system, is explained with the help of a PV diagram and a TS diagram. The system consists of a cylinder with two piston, one cylinder with two piston, right, on each sides of a regenerator in the middle. So, there is a regenerator in the There is a regenerator in the middle. The regenerator which is there in the middle acts like a temporary storage of thermal. So, this is regenerator which is a stationary one, which is inside stationary, right, it is not moving. All the thermodynamic processes of Stirling cycle are shown in the PV diagram and the TS diagram. So, 1 to 2 there is a heat in, and then 3 to 4 there is a heat reject, right. So, 2 to 3 and 3 to 4 are adiabatic cycles. So, 4 to 3 to regen and 2 to 3 also regen. And here V equal to C, V equal to C. In this process, the working gas is heated. The gas, air which is there, is heated, right, which while it contacts with the heat source at constant temperature TH. As the gas expands, it absorbs heat and does work by pushing the piston outward. So, when the heat is given, this fellow expands. So, this piston is dragged along this direction. It absorbs heat and does work by pushing the piston outward. Since the temperature stays constant, because it is isothermal process, the heat added is fully converted into work and the pressure of the gas decreases as its volume increases. So, as I told you, there are only pressure, temperature, volume, that is all. If the pressure of the gas decreases as its volume increases, then isochronic process where you have constant volume heat removal. After the expansion, the gas is moved to a cooler region. After the expansion, what is expansion? After the completely dragging outside expansion, the gas is moved to the cooler region, often through the regenerator. So, now cooler region, so it moves to the other side, to the cooler region, and the temperature is reduced from TH to TC without changing its volume. So, whatever is there, it is pressed. So, there is a regenerator, the air goes to the other side. During this step, the gas gives off heat to the regenerator or to the surrounding. When it passes through, the regenerator which is there absorbs heat. Since the volume is constant, no work is done and the internal energy decreases it's entirely due to heat loss. Then let us go to the isothermal compression. Then from the other side you are trying to compress. So, this is regen, this is a piston, this is a piston which is moving, this is also moving. So, from one side to the other side it is going. Now, the gas is compressed at a cooler temperature Tc, it is compressed. As the piston moves inward, the work is done on the gas here, but the temperature is constant. So, the gas releases heat equal to the work input. The process increases the pressure and decreases the volume, preparing the gas to the next phase. So, from here it goes to the next phase. Isochronic process, that means to say where there is a constant volume. In the final process, the gas is transferred back to the hot region. So, it came to cold, from cold it goes to hot region, but the volume is constant, where its temperature increases from Tc to Th without changing the volume. Before also you saw without changing the volume. In 2 to 3 and 4 to 1, there is no volume change. The heat is added here comes mostly from the regenerator, improves the cyclic efficiency. So, since the volume is constant, so no work is done during this process. So, if you go back and try to see the diagram, so you can see PV diagram 1 to 2, then 2 to 3 is Q out. This is regeneration process, Q to regeneration process, then it is rejection, then it is focused on regeneration process. If you draw the TS diagram for this, it is almost the same. So, what are the features of a Stirling engine cycle? It is an alternative version of Carnot engine that comprises of two constant volume regeneration process. Keep that in mind. The process are not reversible. Okay. The weight to ratio, power ratio is very high. So, we always use a Stirling cycle where you want to have weight to power ratio. Okay. However, because of their high efficiency potential and better emission control, Stirling engine with modification has been tried to compete with the petrol engine or diesel engine, but it has not come through so easily. So, if you understand this cycle, we have seen Stirling cycle wherein which we have two isothermal processes and two isothermal. One is isothermal expansion, isothermal compression, isochronic heat removal, isochronic heat addition. So, these are the 4 steps. So, referring to the PV diagram and TS diagram of Stirling engine, the heat supplied is going to be Q supplied, which is from 1 to 2, RT1 natural logarithm of V2 by V1. Heat rejection happens between 3 to 4, it is RT3 natural logarithm of V3 by V4. So, now if you are trying to compare V2 by V1 equal to V3 by V4, so then the final formula will be heat rejection EF. The final efficiency will be efficiency 1 minus Q reject by Q supply. So, which is nothing but 1 minus T3 by T1. It is observed from the above expression, the efficiency of the Stirling engine is the same as that of the Carnot cycle. So, this is the Otto cycle. Otto cycle consists of 2 isentropic and 2 isochronic process. Isentropic is reversible adiabatic process. 2 isochronic is reversible constant volume process. Right. The cycle was proposed by a Frenchman, Duo de Rochas, in 1876 in Germany. The Otto cycle came from Nicholas A. Otto, who built a successful 4-stroke engine in 1876 in Germany. It is an ideal cycle for spark ignition. So, if you see here, so the inlet of air comes through this, okay, and then what happens, the air whatever is there, it is getting compressed and it is moved in front of the piston. So, once it comes into the piston zone, the piston compresses the air. Moment it reaches the top dead center, then there is a sparking which happens. Moment there is a sparking, then the piston is pushed down, the exhaust gas gets exhausted. It is an ideal cycle of spark ignition reciprocating engine. So, the PV diagram and the TS diagram is represented like this. So, you will have 1 to 2 will be a compression, 2 to 3 will be heat input, 3 to 4 will be expansion, 4 to 1 will be Q out. So, Q2 to 3 and Q4 to 1 are there, right. So, these two processes are constant volume, 2 and 3, 1 and 4 are constant volume process. What happens here is a reversible adiabatic process happens between 3 to 4 and 2 to 1 or 1 to 2. So, if you draw the corresponding TS diagram, so between 1 to 2 where there is no change in the entropy, the temperature increases between 1 to 2. Then from 2 to 3 where there is a heat input 2 to 3. So, here what happens, there is a change in S, the S increases with the increase in temperature. Then from 3 to 4 it is again a constant entropy process, and then from 4 to 1 is a constant volume process, right. So, Otto cycle has isentropic compression, constant volume heat addition, it has isentropic expansion, constant volume heat rejection. In this system, the piston moves upward, compressing the air fuel mixture inside the cylinder. The compression happens rapidly and without heat exchange. So, it is pressing in, there is a heat exchange. So, this is an adiabatic cycle. So, the temperature and the pressure of the gas increases significantly. When you try to pressure, the pressure and temperature press, the pressure and temperature goes high. The process stores the energy in the form of increase in internal energy. So, the constant volume heat addition, at the end of the compression, the spark ignites, because when you ignite it is a combustion, there is a propagation of explosive energy moving front. A spark ignites the fuel air mixture, the combustion occurs quickly, right, instantly it attacks, dum, it does it. The heat is added at a constant volume, because the piston is momentarily at the top dead center. This sudden addition of energy causes the pressure and temperature to the gas to rise sharply. So, constant volume when it is exactly there here close by. First is going here, then you are going very close to TDS. So, there you are trying to talk about the combustion occurs quickly. When it is compressed, there is a spark plug, immediately the heat is added at constant volume because the piston is momentarily at the topmost center. This sudden addition of energy will try to next stage expand. So, isentropic expansion happens. The pressure gas now pushes the piston down, doing useful work on the crankshaft. So, now this one when it is pushed down, the crankshaft rotates and then it starts cranking. So, there is an output. This expansion occurs without any heat exchange. This expansion occurs without any heat exchange. So, it is also adiabatic in nature. As the gas expands, its temperature and pressure drops. This is called the power stroke. Isentropic 3 to 4. Isentropic 3 to 4 is a power stroke, right? And then once the piston reaches the bottom dead center, the exhaust valve opens and the gas is cooled. The gas is cooled at constant volume. Exhaust gas, once it goes to the top, so you see inlet coming in, compression, the ignition happen, then there is this valve opening. So, once the piston reaches the top dead center, the exhaust valve opens and the gas is cooled at constant volume, rejecting heat to the surrounding. So, the exhaust gas whatever comes in your two-wheeler, if you try to keep very close to the exhaust pipe, it has a heat. This reduces the pressure and temperature of the gas, completing the cycle and preparing it for the next cycle. This portion is called as power stroke, which is there in the Otto cycle. So, 3 to 4 is a power stroke. 3 to 4 is a power stroke. So, when we are trying to refer back to PV and TS diagram, so heat supplied, Q supplied is going to be 2 to 3 MCV T3 minus T2. Then heat rejection is going to be Q41, which is MCV T4 minus T1. So, the efficiency will be calculated as heat rejected by heat supplied, 1 minus heat rejected by heat supplied. So, 1 minus it is MCV T4 minus T1 divided by MCV T3 minus T2. So, it is nothing but 1 minus, this is very important, 1 minus T4 minus T1 divided by T3 minus T2. So, the efficiency is going to be, so now what are we trying to do? We are trying to take the normalcy, we are trying to take T1 out. So, T4 by T1 minus 1, T2, T3 minus T2 minus 1. So, it is going to be T1 by T2, right. So, as the process 1 to 2 and 3 to 4 are isentropic, T2 by T1 is equal to V1 by V2, that is gamma minus 1, and T3, T4 is V4 by V3 gamma minus 1. So, as the process 1, 2 and 3, 4 are isentropic, you try to get this formula. As V3 equal to V2 and V4 equal to V1, so then V1 V2 is equal to V4 V3. So, that is we will equal to T2 T1 is equal to T3 T4 or T4 by T1 is equal to V3 by T2. So, now this is the Otto cycle efficiency, thermal efficiency, right, which is 1 minus T1 by T2. As the process 1 to 2 is isentropic in nature, you get this formula, and finally, the efficiency which is followed is 1 minus 1 by RC gamma minus 1, where RC is nothing but the compression ratio. What is compression ratio? V1 by V2. So, we have changed this RC. So, the mean effective pressure PM. How do you calculate the mean effective pressure? The mean effective pressure is nothing but work done by volume of sweep. So, that is Q net by V1 minus V2. So, this can be represented a Q supplied minus Q reject is the Q net divided by, then you try to rearrange this, you get it. So, Q supply is nothing but 2 to 3, you supply MCV and then reject is Q41 MCV T4 minus T1. So, V1 is expressed as MRT by P. So, it is nothing but PV MRT, that is a formula. So, V1 is nothing but MRT by P1, V2 by V1 is equal to 1 by RC. So, V1 by V2 is RC, it is 1 by RC, that is what we are seeing, right. when we look at the PV diagram, so you can see here 3 to 2 there is a Q to 3, there is a heat in, and there is 1 to 4 there is a Q out, 1 to 4 there is a Q out. Upon substituting PM all these things, and PM is nothing but MCV, all these things, you get to this equation. Now rearranging all of them, we try to get into this equation. So finally what you get is this, right. So here you can see R is nothing but Cp minus Cv, RCV you can try to gamma minus 1, and R is this. So now PM can be expressed like this. As the process 1 to 2 and 3 to 4 are isentropic, isentropic means constant volume, V3 equal to V2, V4 equal to V1. Now when you resubstitute in this equation, you get T2 equal to T1 into RC gamma minus 1. So this it can be represented T2 by T3 equal to T3 by T4. So that finally boils down to this. So all these things, equations are very important, so you are supposed to keep in mind. So as the process, so here we are trying to talk about 1 to 2, 3 to 4. Between 2 to 3, it is isochronic process. So isochronic process means P2 T2 is equal to P3 T3. So T3 goes here, T3 by T2 is equal to P3 by P2. So this is alpha. Alpha is the explosion ratio. Now substituting it back into equation 2, this equation, so we try to get this one. So finally PM, which is there, which is nothing but the mean effective pressure for a Otto cycle, can be got by this formula. So when we try to plot the efficiency between compression ratio and efficiency, you can see here the compression ratio for air when gamma equal to 1.4. At the exhaust gas, the gamma is equal to 1.3. In a monoatomic gas, the gamma is going to be 1.67. So this is what people are trying to play with and try to get the efficiency higher. So the effect of CR, compression ratio, with respect to gamma efficiency of a Otto cycle is showed here. Thank you very much.